Hello everyone, welcome to this video. So in the last video we have studied about this theorem where A is given to be an element which has order n and k is some any other positive integer. In that case we have the subgroup generated by a to the power k is equal to the subgroup generated by a to the power GCD of n with k, right? And the order of the element a to the power k is equal to n divided by the GCD of n with k. So for the proof, we'll be first proving this result over here. For this, what we do, for the sake of convenience, we write this GCD of n with k as d, right? If d is the GCD, then you can write this k as this GCD multiplied by some integer that we can do according to the definition of GCD. So therefore, in this case, our element a to the power k, it would become, now in place of k we may write dr, so it becomes dr, and we may also write this to be a to the power d to the power r. So you see, we have written this a to the power k as a to the power d raised to some power, right? So that means this is written as some power of this number. So that means the subgroup which is generated by a to the power k is contained in the subgroup which is contained in a to the power d. So let's mark this as equation number 1. Now if you remember, in the very starting when we were discussing about the basics, we study about the GCD theorem, right? According to this GCD theorem, we would say there would exist integers, say s and t, such that this d could which is the GCD of these two numbers n and k, right, that could be written as the linear combination of n and k. So d could be written as sn plus tk. So that we have a to the power d as, in place of d we are writing sn plus tk, right? We can separate out the powers here, right? We can write this number as a to the power n to the power s, a to the power n, because n is the order of a, so it is equal to e. So we have e to the power s, e to the power s is e only, and e multiplied with some other element is that some other element, and you can write this as a k raised to power t. So that means this element here would definitely belong to the subgroup which is generated by a to the power k, right? So from here we now know that because this was some arbitrary member, so therefore the subgroup which is generated by a to the power d is contained in the subgroup which is generated by a to the power k, right? So let's mark this as equation 2. Now you may see that from the equation 1 and from equation 2 we have the equality of these two subgroups. And what was d? D was nothing but the GCD of n and with k. So this is what we wanted to prove in the first part. So this first part is completed. Now next we have to prove that the order of the element a raised to power k is equal to n divided by the GCD of n with k. So for that, in order to prove this thing here, we firstly show the same result for the case where d is some divisor of n, right? So we will prove that the order of a raised to power some divisor of n is nothing but n divided by that particular divisor, right? So we firstly prove this thing. For that, what we do, we consider a to the power d raised to power n by d. Right now, because we wanted to tell that the order of this thing is n by d, so according to the definition, if we take this element and we raise it to the power n by d, so it should come out to be identity, and n by d should be least of such kind. If this happens, then the order of a to the power d is n by d. So let's take this thing a to the power d raised to power n by d. So you see this d and d cancel, so we are left with a to the power n, and you know already the order of a is equal to n, so that means a to the power n is equal to e. So that from here we obtain this thing as equal to e. This thing is true. If this is true, that means the order of this a to the power d is less than equal to n by d. Now because why this is not equal to n by d, it is because we obtain identity for this case. There may also be some integer for which we would have again the identity which is smaller than that, but you know, order is the smallest integer, but we are not sure that this n by d, this is the smallest of such kind or not. So that is why we have used this inequality over here. So in order to surely suggest that this n by d is exactly the order, so what we suppose, we take some integer I which is less than n by d, and we will prove that when we raise a to the power d to the power I, right, this cannot be equal to E, the identity of the group, right? If that is so, in that case no such integer exists, so that means the order has to be equal to n by d. So for this we consider I as the positive integer which is less than n by d, so that if we raise a raised to power d to the power I, this is not equal to identity. Why this is so? Because you see I is less than n by d, so you can multiply this d onto the left hand side, so you have id less than n, and n is the smallest positive integer such that a to the power n is equal to d, right? So that means id which is lesser than this, if we raise a to the power id, it cannot be identity according to the definition of order. So if this cannot be identity, it means that no such I exists such that it is less than n by d, and when we raise it to the power I, it is equal to identity. This is not true. If this is not true, so that means the order of a raised to power d should be exactly equal to n by d, right? This is one thing. Now, but actually what we wanted to prove that a to the power k, where k is any integer, is equal to n divided by the GCD of n by k. Now we have proved a special case that for the divisor d of n, this result is true. So making use of this result, let's see how we can proceed on to the final result. So applying the same result with taking d as the GCD of n with k, what do we have? Now you know from this result that we have studied in the previous video that the order of an element is equal to the order of the subgroup which is generated by A, right? So this thing, they are equal to each other. So using this fact, the order of a to the power k is equal to the order of the subgroup which is generated by a to the power k, right? So here from the first part of the theorem, we may apply this result that using the first part here, the subgroup a to the power k is equal to the subgroup generated by a to the power GCD of n by k. So using this fact here, we have this thing as equal to this thing, right? Now this thing, because again using this result that the order of the element is equal to the order of the subgroup which is generated by A, they are equal to each other. So this so that this thing would be equal to this thing according to this result. And moreover, if we apply the same result, because you see D is, we can apply the same result here onto by taking this d as the GCD of n with k, such that we have a raised to power d or order of a raised to power d as n by d, right, where d was any divisor of n. So we can clearly apply it with the GCD because that is also a divisor of n, right? So therefore taking this particular case, we have the result that this thing is equal to n divided by this d, and d here is GCD of n by k. So we have our final result with us. So this is the proof of this theorem. Well, that is it for this video. Thank you for watching.